Hey everyone, welcome back to my channel. Today is a special day because I'm launching my very first video tutorial on machine learning with C++. This video is divided in two parts. The first part we're building an ETL and the second part we're building a linear regression model, which we're going to apply on top of the wine dataset. All the references and links are under the description section. You're gonna find there all the code on my GitHub, and you're gonna find where to locate the dataset as well. I want to dedicate a special thanks to everyone that has supported me so far via Patreon. People like you make these videos happen, and I really hope you enjoy this one. The first class that we're going to be working on is called ETL, which stands for Extract, Transform, and Load. And basically, it will provide us with an API to read data from a CSV file. For this tutorial, as it is the first one, I will not build anything extremely difficult, as I want you to start by doing something very easy in C++, so you wouldn't be scared of the language. And with the next tutorials, then we can start building more complex functions. So let's start by including the necessary packages that we're going to use. The important package here is Eigen. I like to see Eigen as the NumPy for Python if you're more familiar with Python language for machine learning. Eigen is basically a C++ template library for linear algebra, so it is going to help us manipulate matrices in an easy, fast, and elegant way. When including your Eigen package, this line of code can differ from mine, so make sure that you have the correct include when trying out this code. Our ETL class will accept a file name as a string. This is basically where is your dataset located and the name of the dataset. Delimiter, which will indicate whether our columns are separated by a comma or a semicolon, for example, and a header flag, which basically indicates whether we have a header or not. So we're just going to quickly include that, and this will be our constructor arguments. So let's just code that. Now we're going to focus on building our member functions of our ETL class. For this, we go to our implementation file and we include our necessary libraries. Plus, don't forget to include your header file inside the implementation file. The first member function will parse the content of a CSV file line by line and store data in a vector of strings. We're going to use ifstream to open our file for reading purposes only. We are going to need a vector of vectors of strings, which is basically where we're going to store our data and return it. And now we're going to iterate through each line and split the content using the delimiter that we provided through our constructor. Now we're just going to close our file and we're going to return our vector of vectors of strings. To test our read CSV function, we will create our main file, which we're going to call it simply main. And we're going to include our ETL header file plus all the necessary libraries. We are going to create an object of ETL, which will include the 3 input arguments, so the file name, delimiter, and the flag. We are going to get data from the CSV file using our function declaration for the read CSV that we just built. And we're just going to say return exit success. And we're going to compile this in our terminal and run it to make sure that everything is fine. Our second member function for the ETL class will now store the vector of vectors of strings as an Eigen matrix. So we're going to call it CSV to Eigen, and we'll build basically a matrix based on the input data. Our function will have as input the vector of vectors of strings. We're going to have the amount of rows, and we're going to have the amount of columns of our data. If you're more familiar with Python, this will be similar process as using pandas to create a data frame. You're going to see these similarities once we're going to test this function. So we're going to use the header flag to tell our program that if it's true, then we're going to remove it, because we don't really want to manipulate our data with the header. We just want to manipulate the raw numbers from it. We're going to create an empty matrix with Eigen of the size of our columns by our rows. And we are going to start iterating our columns and our rows. So we're going to start iterating over our empty matrix, and we're going to be filling it with the numbers. Okay, so we're going to fill it with the numbers that we're going to convert from the strings. Remember that we basically store strings in a vector and that into a vector. So we have to transform our string numbers into float so we can manipulate them afterwards. And we are going to return the transpose of the matrix to have the rows by columns. Of course, you could do this in a different way, so you could just do rows by columns in the first place instead of columns by rows, but this was more convenient for myself. Now let's test if we have successfully implemented our CSV to Eigen function. We are going to first define the amount of rows and columns based on our input data. And now we're going to use our dataset vectors of strings and our rows and our columns to call our CSV to Eigen function. And now we're going to test, compile and test and see that we don't have any typos or any problem. Now we can just easily print our matrix, compile and test, and that's about it. We can see here our data frame. Soon we're going to start developing our first machine learning algorithm, which is going to be linear regression. And we are going to be using our red wine data, which also means that we're going to be performing linear regression on multiple variables. Because of the nature of the linear regression model, if we have variables that are in different units of measurements, one variable could favor another variable. Therefore, we first need to standardize our data by bringing all variables into the same order of magnitude and centered at 0. We are going to build a normalization function based on the set score normalization. For this, we're actually going to have a total of 3 member functions on our ETL. So we're going to have the normalization, and we're going to have 2 helper functions. There's going to be one that calculates the mean and another one that calculates the standard deviation. We're doing this so later on, if we would want to denormalize back to the original data when making predictions, it would be way easier to do. It's fairly easy to calculate the mean of our matrix in C++. We will define a mean function that will take the matrix data as input and return the mean of each of the columns, which correspond to each of the variables, so the mean of each of the variables. We can just directly say that we want to return the mean of each column in this way. Sometimes in this language, the return type is not that straightforward to know. So if you don't know what type of data you're returning, you can just make use of this function that declares the type of an expression for you. The standard deviation can be a bit more tricky to implement from scratch, but if you look closely to the function on the right, I would explain you how we can relate this piece of equation to the code that we're implementing. So the difference of each observation from its mean is what we're going to call here data in this function. And based on the formula, we're going to calculate the sum of the square of this difference. And then we will basically divide this result by the amount of rows minus 1 and take the root square of all that. Now we just need to simply apply mean and standard deviation to our data, and so we can normalize it. So first we calculate the mean. Then we calculate a variable called scaled data, which is the difference of each observation by its mean. And we're just going to use that scale data as the input to our standard deviation function. And then we're just going to apply the normalization. So we can just say divide our scale data, as you see in the formula on the right, by our standard deviation. Let's just test quickly our normalization function just in the same fashion as we tested our CSV to Eigen function. Now you can see the result of our data frame, which has been normalized. If you're familiar with Python libraries for machine learning, such as scikit-learn, you will probably have already used a function called train test split, which basically splits your data into train and test sets. And that is what we're going to build right now in our ETL class. The way we're going to make our C++ function is to return 4 different Eigen matrices by wrapping them into a tuple. Our input is going to be, of course, our data matrix, and we're going to specify the size of our train set. With the size of our train set, we can calculate how many rows we're going to have for our train data and how many rows we're going to have for our test data by basically subtracting the train rows to the total amount of rows. With Eigen, we can make use of block operations, so we can easily tell our program to take the top rows for train set, for example. So we just indicate how many rows we want, and it would just take from 0 to the amount that we're just specifying. And then once we have the top rows, we can select the left columns corresponding to the features. So we're just going to specify total amount of columns minus the -1, which would be the latest one, the last one. And we're just going to say that our Y train will correspond to the right column, and we're just going to specify 1 because we only want the latest column to the right. This is obviously the same for the test set. So in the same fashion, we're just going to use bottom rows instead of top rows for it. And another thing is that normally you have a CSV file where the output it's always to the far right, but if it's not like that, then you will have to make changes to this code. And then we're just going to return our tuple, or make the tuple with the 4 different Eigen matrices with our data already split. So let's just quickly test our function to split the data. And we're just basically going to first declare our 4 matrices, so the train features, train output, test features, test output. Then we're going to make use of the function, again in the same fashion as we have been doing before. And we're going to use tie to basically unpack our tuple. The way I'm going to test this is basically by logging the size of the different sets, so you could get an idea. So we should have I think it's 11 features for train and test features, and then the corresponding amount of rows, and then obviously just one column for the output and the same amount of rows as the corresponding train and test sets. So you can see here our train rows 1279, X train calls 11, and the Y is the same amount of rows and one column for the Y. And we're just going to do the same for the test. For the tests, we have less rows, but the same structure as for the training. Finally, we start building our first machine learning model. So we're going to create a linear regression class for this with its corresponding implementation and header files, and we're going to define the constructor and import the necessary libraries. The first thing that we have to keep in mind is that linear regression is a statistical method that defines the relationship between independent and dependent variables. The idea is to fit a linear model to our data. If you see the equation on the right, being x the independent variable and y the dependent, our goal is to find a slope m, which is the steepness, and the y-intercept, which is b in this case. This is the value of y at the point where the line crosses the y-axis. We have different methods to calculate this. We can use the ordinary least squared OLS method. This method is simple and is computationally inexpensive. This would be optimal solution for not very complex datasets. If we, for example, have a multivariate dataset with multiple dependent variables, we will be required to use a machine learning algorithm called gradient descent. The gradient descent goal is to minimize the cost function. If you're not familiar with this optimization algorithm, don't worry, we will revise the equations before implementing it. Let's modify our linear model and represent it as the equation below. This is what we call the hypothesis function, represented by h. The goal is similar like the above operation that we did to find out a best fit of intercept line y and the slope m. Using gradient descent algorithm, we will figure out a minimal cost function by applying various parameters for theta 0 and theta 1 and see the slope intercept until it reaches convergence. So let's recap. Theta 0 represents our y-intercept. We let x0 be 1, and theta 1 is our weight on variable x1. With these conventions, we can generalize and rewrite our equation as, where m is the number of input variables, j is the feature index, x is our data, and theta is a vector of our weights. Okay, so now we have to train our model. Training involves minimizing some cost function. And in this way, we can measure the accuracy of our hypothesis function. A cost function is just really how we penalize the model for making an error. In our case, we will define our cost function as, this cost function takes the difference in the predicted value from our hypothesis and compares it to the target value. This difference is then squared and calculated for each prediction output combination and then summed and divided by 2 to give the mean squared error. This is basically the ordinary least squares procedure and is generalizable to multiple input variables, making it very useful. So let's then compute the OLS in our C++ class. So we're just gonna implement a float function. We're gonna take as input our x, our y, and theta. After having our OLS function, now we have to provide the program with a function that provides our algorithm an initial for theta, and that will be changed and updated iteratively until it converges at a value that minimizes our cost function. So I just basically described gradient descent. So gradient descent works by calculating the gradient of the cost function, which is given by the partial derivative of the function. We have another parameter that's important in gradient descent and is denoted by alpha. This is often called the learning rate, and it tells the algorithm how quickly it should move. So if you move at very small steps, you won't get anywhere very quickly, and you might find a local minimum. If the steps are too big, you might not even find at all the lowest point. This symbol means that we update the value on the left at the same time we calculate the values on the right. The inputs to our gradient descent algorithm will be x, y, theta, alpha, and the number of times we update our theta until it converges. So I'm going to quickly code our gradient descent function, and then I'm going to go step by step with our equation on the right, explaining what does each step does. We define temp as basically a placeholder matrix for theta. The parameter denotes the amount of variables we have, so the amount of features. We define a cost vector where we allocate the initial cost and that we will be updating with our new weights. Now for each iteration, we're going to calculate the error function, which we use to multiply each feature to obtain the error of each of the features, and we use the placeholder term to allocate it. Then we update the theta and we calculate the new values of the cost functions based on our new weights. So now we're going to test our linear regression model. So we're going to have to define a vector for train and for test set of ones, which is going to correspond to our x0. We have to resize our matrices so we can allocate this vectors of ones in our data set. Now we're going to design our vector theta that we're going to pass through our gradient descent algorithm. Basically, it's just going to be a vector of zeros of the same size as the train data set, then our alpha and our number of iterations. We're going to define our output variables, so theta out, which is going to be the coefficients, and our cost vector. And the same procedure as with the train test split, we're going to use the tuple function that we have created. And we are going to make use of our gradient descent algorithm and get the outputs. So you can see here, this would be our coefficients for each of our variables. So for each of our features. And now we're just going to print out our cost function or our cost vector. And you can see how it would be decreasing. We're gonna plot this later on. We're not going to be plotting anything in C++, as I consider that Python is the best option for this. So what I'm going to do is just create two functions to basically export our data, and we're going to use the exported data into a Jupyter notebook where we're going to compare our results and plot, for example, the cost function. So now we're going to export our theta out and our cost function. To see how good the fit is to our data, we can calculate R² value, which is given by the equation on the right. So we're just going to code this, and well, this corresponds to the mean of the observed data, and y hat is the predicted value. As mentioned before, we calculate again our mean and our standard deviation based on our data, because once we're going to calculate y hat, we are going to denormalize the values so we can calculate properly R². So we have a poor value for r-squared, but this doesn't really mean that our algorithm is wrong. It could be because we didn't really do any feature engineering before applying our algorithm. We just did everything with with the entire data set. And now we're just going to compare our algorithm from scratch with C++ with the scikit-learn algorithm in Python. So I have created this Jupyter notebook for linear regression, which you also have available on my GitHub. And basically I just imported the data as normally, and then the exported white train hat, I'm going to use it to compare to the predicted values of just the y from the linear regression model from scikit-learn. So here I just plot our cost function from our scratch model, and you can see here that our model is practically identical as the one provided by scikit-learn. This will give you also an idea on how these Python models are built internally in scikit-learn. Thank you very much for watching. Don't forget to share this video, subscribe and like it, and I hope to see you in the next one.